Well, welcome everybody. I'm glad you could make it here tonight. I want to introduce myself before we get started. I'm Jason Hepler. I'm the Digital Engagement Librarian here at UNO. I've been here since January, so I'm fairly new to this university. But lived in Nebraska for a long time before this, so not too new. I'm also an assistant professor of history. I have a courtesy appointment there, so there'll be at some point in this talk some history because I can't help myself. But I want to talk tonight about data visualization. And so the agenda tonight is to think about what this thing is that we call data visualization. We're going to look at some different types of data visualization. Talk about some design principles and things to think about when you're visualizing data and evidence. And then look at a few examples and tools. We'll talk about some tools, and time permitting, hopefully I can guide you through a couple of tools at the end. So to get started, I always start here when I talk about these things. Edward Tufte, for those that don't know, is sort of a fairly large name in information and data visualization. He's responsible for popularizing a lot of these things. You'll find he's got 4 really nice big books that he sells that have all sorts of stuff in them about the history of data visualization, what works, what doesn't. It's a good set of books. But I like his recommendation here when it comes to thinking about what we do with graphics that we make for visualizing data. And he says that we want things that give the greatest number of ideas. So we want visual things that are good at conveying a lot of information at once. We want people to grasp these things as quickly as they can, shortest amount of time, the least amount of ink. Tufte refers to these as junk charts, charts that have too much stuff on them or obscure things, make it hard to read. So keep the stuff off that doesn't need to be there. This is done in the smallest amount of space, meaning that we can do these things at different scales, right? They could be large visualizations, they could be much smaller, and which tells the truth about data. Now, I quibble with a few things in this here. I'm not so sure that there's a truth to data, for example, but I think Tufte's ideas generally hold pretty well. So we want things that are understood by our readers, whether that means we're annotating visualizations, we're using good labels and so on. We want design that does not mislead intentionally or otherwise. And we want visualization to design that gets the point across. Right? Visualization is not about pretty pictures. It's about identifying patterns. It's about communicating things. It's about exploring your data. So why should we visualize? Well, there's 2 reasons mainly. One is to, as I just mentioned, explore your data and your evidence. So it may be that you are looking for patterns in something. Visualization is one way to identify patterns in your data or identify problems with your data. Another reason would be to communicate the results that you're seeing. Oftentimes, data visualization and graphs and charts and so on work better than charts of tables, right? They're hard to read for some people. If you're not a domain expert, that can especially be hard to read. But graphics can help us communicate with a broader public. And there's generally 3 types of visualizations that we can kind of categorize these things into. The first, and the one that we're going to focus on tonight, is called information visualization. These are often statistical charts and graphs, but they can also be other visual or spatial metaphors, so maps, for example. So this is the visual representation of data itself. There are scientific visualizations. These are visualizations that have close ties to real-world objects that have spatial properties. So, for example, you might think about modeling the airflow over an aircraft wing. This is that kind of visualization. And then finally, I'm sure many of us have seen the infographic, combining statistics and visualization with a narrative. Sometimes these are rather polemical, but they usually have some kind of story that they're telling within them. I'm not an expert on infographics, but we could talk about them. As I said, tonight will be mostly about information visualization. So before I go too far, I'm going to return to Tufte's ideas that we started at the beginning, and I want us to be thinking about the critical engagement that we do with visual argumentation. And I think one of the ways that we get there is by understanding certain principles that undergird the perception of graphical elements. And what I mean by that is that our brains have rather particular ways that we interpret visual elements. This is referred to as the Gestalt principle of data visualization. Gestalt is a German word for pattern or form. And I want to talk about three right off the bat here that I think meaningfully impact the creation and interpretation of visualizations. And as I said, Gestalt refers to this ability to see the whole from the parts, right? We're really good at finding patterns in things. Our brains are really good at it. And this is why visualizations work. Otherwise, we wouldn't be able to identify patterns, or we wouldn't be able to notice where there aren't patterns, where we might expect them. So these principles, these Gestalt principles, are both pragmatic and practical for data visualization. So, as an example, let's imagine that these dots up here are data points of some kind, okay? The first principle we can talk about is what's called similarity. These are elements that have shared visual properties that we would consider, automatically we consider part of the same group, right? So the groups here, of course, are red and gray circles. And our brains are making this connection that says, okay, everything that's red must belong to some kind of group, everything that's gray must belong to the other kind of group. But note that there is an implied problem with this graphic, which is the implication that there are rows and columns. That's not the intent here, but it's an important point because we're unintentionally conveying some meaning through visual form. Okay, so similarity. The other is proximity. These are elements that exist close to one another. It's another indication of similarity. And we can see here these groupings of circles, the circles on the left and the circles on the right, which imply that these two groups have something in common, something, in other words, that makes them distinct from one another. And I want to pause here to focus on what this means for visualization because, especially with more complex visualizations, we're going to look at network graphs in a little bit, for example. Proximity does not mean similarity in those cases. Instead, we see similarity conveyed in a network through connections among lines and circles. And it's a difficult problem to solve in data visualization, but we have to consider it when we're analyzing these visualizations or trying to communicate with visualizations to our other audiences. But we'll talk about that in a little bit. The final one I want to bring up is what's called closure. You undoubtedly looked at these two shapes and completed them. You saw the circle, you saw the rectangle. With closure, humans perceive objects as shapes, letters, pictures, as being a whole even when they're not complete. So when we look at shapes with missing segments, our brains make a connection that completes the shape for us. So we perceive a circle, we perceive a rectangle. We don't see these as random lines on a screen. And I pause to talk about these principles because I think it's important for us to be aware of the unintentional value that we encode in visualization. Our readers see shapes, they see proximity, they see color, they see animations, and these send signals that may be unintentional byproducts of palettes or layout or so on. So effective design, in other words, of complex visualizations must consider some of these principles and the signals that our graphics are sending to our readers. So it's time for a quick quiz. Can anyone tell me what's wrong with this graph? Just shout it out if you have an idea. There might be a couple things. The scale is weird, right? Right, that's right. Yeah, so there's no y-axis. We don't really know what's on the y-axis. It's probably not built off a common baseline. This probably isn't 0. Or if it is, the scale between this line and this line is incredibly compressed while the rest stretches out. Because 6 to 7 million really isn't that big of a gap in the grand scheme of things. And just so I don't just pick on Fox News, what's wrong with this graphic, these bar charts?
It almost looks like 100%.
That's right. 53% is the new 100%. Yeah, there's also 90% missing in here, or 10% missing in here, which is kind of weird. There are better ways to represent this. I think what they're trying to show is some proportion of percentage, which would work better if you were to stack all three of these together and show 100% and then break it down. But, it's encoding something, right? It's making it look like white voters are overwhelmingly, in this case they are overwhelmingly, but it implies something greater than what's actually here in the data. So while we're on this topic of visual cues and perceptions, I want to note just a couple of other really quick things. So in the mid-1980s, two statisticians did these experiments on people, and they sat them down and had them look at different graphical elements and asked them what they were perceiving, how well they could predict, or not predict, but interpret what was trying to be represented in the visualizations. And I just want to point out a few of their findings, just so you're kind of aware. So one is that humans, it's very difficult for us to compare length judgments without a common baseline. So the top one there on this graphic, at the very top, that bar chart, it's pretty easy for us to see the different lengths and what's going on. The next one down, where it doesn't share a common baseline, it's kind of hard, right, to see what the far left and far right bars, are they actually close in length? It's kind of hard to tell without sharing a common baseline. Two, people misjudge area easily. Area judgments tend to be less accurate than length judgment or position judgment, so a scatter plot works well, for example. People misjudge volume even more, which is why 3D charts are terrible. Don't ever bring me a 3D chart. I will throw you out of my office. Excel does this. They do 3D bar charts and 3D pie graphs. But they're bad. They're bad for perception. Speaking of pie charts, people misjudge angles as well. We often underestimate acute angles in particular. Pie charts are awful. Try not to use them. People find it hard to judge slopes and changes within slopes. So we're kind of going down the graphic here. Line graphs work pretty well depending on what you're trying to visualize. But there might be areas where you're looking at angles. Again, with pie graphs, they're very hard to see and perceive differences within the slopes. Comparisons, of course, cannot be made if people can't see the data points. So if they're obscured or they overlap in some way, it becomes hard for people to compare data. And finally, colors are good for distinguishing categories, say apples and oranges, or different types of fruits, but less useful if the values are continuous. So if you were looking at, say, date of harvest and expiration date, where there's maybe some new number every day for some length of time. We could encode some of that with color, but at some point you get too many colors. The human eye can only distinguish, I think, between 5 and 7 colors meaningfully in any visualization. So if you're doing too much color intensity, it becomes washed out. It's too hard for people to read. All right. So I do want to step back here and look at a few examples. Talk about some things that people can do, what people are working on these days. Then, as I mentioned, we'll look at some tools for starting visualization. But of course, I would be a terrible historian if I didn't start at the beginning. Well, not the total beginning. Maps, of course, have been around for centuries. I won't go back that far. But I do want to stop in the 18th and 19th centuries. And I want to point these out because it's important to realize that most of the data visualization practices that we use today are only about 150 years old. They're pretty new in the grand scheme of things. So I want to note a few names and a few techniques here. And the first here is Joseph Priestley. Joseph Priestley was an 18th century polymath who created a book called The Chart of Biography in 1765 that he believed, quote, would trace out distinctly the dependence of events to distribute them into such periods and divisions as shall lay the whole claim of past transactions in a just and orderly manner, end quote. And the entire chart, so we're looking at a subsection of the chart here. And what you're seeing are people's names, and the line underneath the name is their lifespan, right? So date of birth to date of death. The entire chart, if we were to show you the whole thing, covers a very vast period from 1200 BC to 1800 AD. Includes over 2,000 names on it, and these names are categorized by types of people. So, and he broke them down by statesmen, divines, mathematicians, poets and artists, orators, and historians. In 1769, he also released what he called the New Chart of History, which I don't have an example of right off hand. I could find it later, which attempts to illustrate the whole of world history, which is a very ambitious thing as well. But I mentioned Priestley here because we still see this kind of visualization. It's innovative for its time, but this kind of swim lane timeline view that we have is something we still use today. It was brand new in 1765. We also have to talk about William Playfair, who was an engineer and a political economist who's considered the founder of graphical methods for statistics. Playfair invented many of the diagrams we use today. Line charts, area charts, bar charts, pie graphs, they all come from Playfair. All of these were invented between 1786 and 1801. Playfair takes inspiration in part from Priestley's chart of biography. This is how he gets to the bar chart, is by looking at Priestley's timelines. But he's also very innovative in some of these other graphics. So looking at, for example, differences in trade between two nations, and doing these kind of area charts to illustrate the balance of trade between nations. I also want to point out the work of John Snow, not this one, but this guy. John Snow was an English physician working at a particularly fraught time in London during an outbreak of cholera, which swept through the city in 1854. Snow began charting with bar charts on a map the location of cases of cholera. And Snow found a cluster of cases around a single water pump in London. And using this map and statistics, that he links the outbreak to the quality of the water. He overturns a prevailing theory that cholera was an airborne illness. And it's through this that Snow actually becomes sort of the founding father of epidemiology as a field of study. I should note that Thomas Shapter, who also living in London, produced a very similar map in 1849, I think. But he doesn't make the connection between the water quality and the outbreaks. Finally, how many have seen this graphic before? Anybody? Really? Wow. That's amazing. This is the work of Charles Joseph Menard. This is probably one of the most famous information graphics in existence. It was cited by Edward Tufte as the best statistical graphic ever drawn. It's probably a little hard to read up here. What Menard is trying to illustrate is Napoleon's march to Moscow. Okay, so here we are where it starts. The width of the band indicates the size of his armies. So as he's marching to Moscow, it gets smaller and smaller. They fight, it shrinks, and the army shrinks ever so smaller as it retreats back to France. There's a lot of information here. There's time, geography, so a lot of these are place names, sort of put in relatively close geographic space. Loss of life, of course, the shrinking of the bands. Temperature, so Menard is making some kind of correlation between how cold it is and the shrinking of the army as it retreats. Geography, as I mentioned, and some historical context. All in one graphic. That's a lot of stuff to put in one graphic. If you have a chance, look it up at home, check it out, it's really cool. Okay, let's talk about a few things going on today. First, of course, is the time series graph. This is pretty self-explanatory. This is looking at data that changes over time, right? In this case, looking at daily temperatures and their averages between New York and San Francisco over some length of time. If you're working with time series data of any kind, whether that's hourly, daily, monthly, yearly even, could get away with it. This is a really good way to represent some of that data. This particular graphic, not here, but if you were to look it up online, is also interactive. So one is if you mouse over these lines, you see the data itself. But also down here, you get this contextual timeline. And online, if you were to grab one of these handles and draw it in or draw it out, it'll help you zoom in and zoom out on the data. So you get these different kind of views into what's going on within the data. Another kind of way of looking at change over time is the stream graph. These views attempt to show proportion and change. In this case, countries winning Olympic medals. I think this is a really interesting graphic. I think it does an interesting job of trying to say something about the countries that are winning these. I think it's also very good, even though it might be hard to see, it's very good at annotating what's going on, right? So these gaps, for example, are the two world wars. And then, of course, when the Soviets win all these medals, the US is boycotting the Olympics. And when the US wins all these medals, the Soviet Union is boycotting the Olympics. So it does a good job of annotating what's going on, helping orient the readers within, different historical changes. Heat maps are another way of kind of representing change over time, but that's not their only purpose. Heat map works like a matrix. So it's looking at some point A and point B, and it's looking where those things meet. And where those things meet is some kind of value. The higher the intensity of the value, the higher intensity of the color. So in this case, the more orange it is, the more number of cases of measles. The smaller the number, the less intense that is, in this case, dropping closer to blue. If anybody in here uses GitHub for code or anything like that, you've probably seen some of these. You get like these calendar views that show you code commits, for example. The more code you commit, the brighter the square. But there might be some other ways that you could see using something like this in your own data. Maps, of course, I don't have to spend too much time on maps, but of course we can represent spatial information. Here looking at county and voting districts. There's a lot of good tools for doing this kind of thing, which we'll look at. This here is called a tree map. A tree map is interesting. It tries to visualize the parts from the whole. In this case, looking at business sales, I think. Yeah. Color indicates region, so south, east, west, and central. And then the proportion of the individual squares indicate number of sales for a particular office. So it's an interesting way of trying to see how things break down within a whole. At some point, though, if you have a lot of data, this becomes impossible to read, right? The squares are going to get too small, you can't really read them. So there's I think, a fairly limited purpose to the tree maps, excuse me. But there it is. Similarly is the radial graph. This is also kind of looking at sales, so we could see like fourth quarter has a really good quarter. We could see how the month breaks down. These all have different sizes. And then see which cities are contributing to that particular region, or that particular quarter. This does look suspiciously like a pie graph, so I would urge you to think differently if you were to do something similar. I could see doing this as a bar chart and getting the same point across very easily. Still using the same data and the same kind of color palette, we could do this as a bar chart. This is called a Sankey diagram, and it's used for charting the flow of values. So width of bands in this case indicate a value of some kind, right? So there's a large amount here, and then they branch out into other things. This one's looking at energy, I think, and who uses it. I've seen it used for internet traffic. I've seen it used for transportation traffic. It's a kind of network in a way, where you have connections between individual nodes within this thing. But if you're looking at flows of data or flows of information, the Sankey is an interesting way to do it. This also should look somewhat familiar, because this is essentially what Menard was doing with the Napoleon map, where the bands indicate some kind of different values. And finally, I just want to point out network visualizations. Using the methods of network statistics to represent relationships among entities. These entities could be people sending letters back and forth or emails back and forth. Different nodes on the network could be places and travel between these places. They could be computer networks and connections among networks and computers. Lots of things can be represented by networks. I teach a few workshops on network analysis, so if you're really interested, let me know. We can talk. But there are really endless ways to visualize this data. Lots of ways to take data and convert it into some kind of graphical representation for the purpose of identifying patterns. And of course, if you're going to do that, you have to think about your data. Data usually comes in one of two forms. There's discrete or categorical data, right? So apples and oranges. And then continuous data, which is continually being measured, something usually measured. In this case, let's say date of harvest and date of expiration. That would be a continuous value of some kind over some period of time. Each would result in different kinds of visualizations and would require different ways of thinking about how to prepare that data. Can you read this okay? Okay. So I want to mention just a few tools and we'll look at a couple because we have lots of time. First one I want to start off with is processing. I will first admit that I don't use processing. I don't know Java as a language, so I can't help you a whole lot if you decide to use processing. But there are some really good projects out there that use it. If it's a tool you're interested in learning, let me know. We can talk. I can help find some resources to get you started. It's not a very interactive piece of data visualization. So if you're doing like interactive data visualization, like on the web, it's probably not the best tool for that, but it's something that we could use and talk about. It does require some programming experience. So again, if you're not versed in Java as the language, the learning curve would be rather steep. D3.js. D3 stands for data-driven documents. I do use D3. D3 is a JavaScript library that adds a whole suite of methods and functions that allow you to build visualizations. The learning curve is rather steep, especially if you don't know JavaScript like I did when I first started. But it's incredibly good at what it does. The community is really vibrant. And D3 does a really good job sort of abstracting a lot of visualization work. What that means, though, is that you're going to spend a lot of time building pretty much every component of your visualization. Okay, so what that means is that D3 isn't set up to say, like, there's no function that says bar chart, and you just throw your data into it and get a bar chart. If you're going to build a bar chart in D3, you're building everything. You're building the bars, you're building the axes ticks, the values on the axes ticks, the labels on the axes, everything. I know that sounds like a pain, but you get a lot of control over what's going on in your visualizations. I can show you one of mine if you're interested. The other one here, R. R is a statistical programming language. And if we pair it with this library called ggplot, this has become a very useful tool for doing data visualization. I'm also an R user. You're a little limited in interaction, so if you want interactive data visualization, ggplot itself isn't designed for that, but there are some libraries that are trying to convert some of those visualizations into web-based graphics. R itself is not a terribly tricky language to get into. The nice thing about doing all this in R, though, is R can do everything from data manipulation and cleanup and visualization, right? So if you're investing in R as a language to learn, there's a lot of payoff, right? Because you can do everything you need to do with data and visualization all in one language. You're not having to learn different languages. I don't have Python listed on here, but Python also is getting very good at doing this kind of thing. I think there's even a ggplot library for Python now. I'm not a Python person, but. And then finally, I want to mention Tableau. In particular, Tableau Public. Tableau itself, I don't think we have a license. And I would recommend you not get one because it's expensive. But if you want to use Tableau, they have a version called Tableau Public that's free. The stipulation, however, is that the data you put into Tableau Public becomes public. Okay? So if there's anything that you have that can't be public or you would prefer not be public right now, that stuff goes onto their servers and becomes accessible. So, bear that in mind. The nice thing about Tableau, though, is there's no programming involved. It's all drag and drop. You load your data in as a spreadsheet. Your columns are just boxes you select. You drag them into place, and it builds the graphics for you. It's pretty cool. It's pretty powerful in what it can do. It's not very flexible. There's not a whole lot of visualizations that you can do. Yeah.
Yeah, actually, Tableau actually is for free for students.
Oh, it is?
Yeah,
The full thing?
Friday kind of free.
Oh, great.
One for the academics and students.
Oh, okay. Oh,
One kind of.
I didn't know.
Yeah, it is not public. It's kind of.
Oh, good to know. Oh, great.
You can simply search kind of Tableau for students and then just it says download Tableau that's for free.
Okay.
You can just try it.
Awesome. Thank you. That's great. Thanks. In case, does the video need that? If you search for Tableau for students, you can find it. It's free. They get the point. All right. Just real quick, I started putting together a libguide on data visualization. It's somewhat bare bones right now, but if you're interested in tools or looking at other examples of visualization or interested in any readings on visualization, I've started putting together some stuff here. And that'll be changing over time as I continue to iterate on some of that. Yes, sorry. I wish I had a better URL for you. I'm sorry. Okay. Well, we've got some time, so we're going to look at a couple tools. These are both the two tools. We're going to look at two tools, at least, maybe more, depending on how fast we get through them. If you want to follow along, you can. There are machines in the back here if you want to follow along and play around with this, but we can also just watch if you want to do that as well. Let me think. Both these tools are web-based and free. So they all take place in the web. You don't have to download any software or anything like that, which is pretty nice. So let's start here with a tool called Palladio. So Palladio, I worked a little bit with this team when I was at Stanford. Palladio is built by a research lab there called Humanities Plus Design. And although this has humanities in the title, I promise you it doesn't just have to be humanities data. So if you're a scientist or anything like that, this would probably work fairly well for you as well. But the great thing about Palladio is it's all web-based, it's all free. And it comes with a few built-in visualizations. So we'll take a look at some of these here. If you were coming into this with your own data, you could drag a spreadsheet onto here or a CSV file onto here. It'll populate it for you, and you'd hit the load button and it would take you in. What I'm going to do is use the sample data. So there's a sample data set here if you're following along on your own machine. We're going to give this a title. We're going to call it Monaco. The data here is aristocrats that were living in Monaco in the 19th century. That my friend Mark Brody put together for his research. What we're looking at here are essentially two spreadsheets. Okay, so there's a spreadsheet number one called people, each with a different column. So each row in here is a column in the spreadsheet, and then a spreadsheet called places, which is simply the name of a place, so the town, and the coordinates for that place. So if we were to look at one of these, so if we click on name, we can see the names within here. Palladio, you'll note, tries to be smart about what's going on in your data. You'll note that little red dot next to the name up there. Palladio thinks there might be a problem. So if you click on this here, what it's saying is that it's found a special character. In this case, it's a dash. Since it's probably someone's last name, it's not a problem. But let's say, for example, you were building your data set and you used, I don't know, like semicolons to separate, multiple values for one thing, and accidentally typed in a colon or just a comma, Palladio would, one, alert you to that problem, and two, if that was the case, you could click on this and it would just take that out of your data set for you and clean it up. It doesn't touch your original data, of course, but it'll correct it on the fly. If you do have multiple values, in this case separated by semicolons or something, you would type that in right here. And Palladio is smart enough to be able to break those out into individual variables without messing with your own data set. So it'll be smart enough to keep everything collected together. I do want to point out also these place names. So in this case, we have a column called birthplace, which are just town names. And if you look down here where it says extension, you'll see that our places table is being mentioned here. And what that means is that we've connected these place names with these place names. So these place names correspond exactly to the other one. But what Palladio is doing is it matches these place names with these place names and then associates a coordinate with that place. And what that means is that you can keep one table for coordinates rather than having several rows of different coordinates in one table. Does that make sense? So if there's a problem, you type in the wrong coordinate or something, you don't have to fix it everywhere. There's just one spot to fix it. You don't have to set up your data tables this way, by the way, but if you need some cleaner way to kind of bifurcate these things, Palladio can help handle that. Well, let's take a look at here. So Palladio comes with a few built-in graphics that you'll see here at the top. Maps, graphs, which are networks. There's a table view, which is just the data listed as a table. And then a gallery view. So if you have images or anything like that that you want to display with your data, Palladio lets you do that. Let's start with a map. And by default, Palladio is not going to do anything with your data. It's not going to make any assumptions about what you're doing. It's not going to try to draw things before you tell it what to draw. It's just going to give you a blank map. And let's say we wanted to map the birthplace and death place of everybody in this data set. So we would add a new layer. And we have our data tab selected here. And since we're doing birthplace and death place, we're going to do a point-to-point map. So we'll get these kind of airline maps to build out of this. Source in this case will be birthplace. Target is place of death. Tooltip refers to hovering your mouse over the line. It'll pop up some kind of, in this case, place name. These could be anything from your data set. If you want to change the color, we could do Maverick Red or something. Show the links, which we want to see the connections. And if we size the points, we can size each place by the number of people, right? So if there are lots of people in Paris, for example, we'll see a larger circle. And if we add this layer, we'll get our map right away. If you mouse over these, well, that doesn't help. You'll see place names. It'll also give a count. So there's 36 people that were born in Paris and moved all over. Now, the real power, I think, of Palladio is not just the ability to quickly visualize something like this, but it's the way that you can cut through your data and get different views on it. So on the bottom here, you'll see that there are three choices. If I can zoom back in. One called facet, one called timeline, and one called time span. So let's start with a facet. Facets are basically the column headers in your spreadsheet. So if we were to choose a few of these dimensions, let's say gender, place of death, position, and birthplace. You'll note down here, now we have these options available to us. We're seeing the data right from our spreadsheets. It's giving us a count, so there are 18 people that were born in Paris. So we're seeing 18 out of the 18 on the map right now. But if we only wanted to see the women in this map, for example, we could click on the F tag here for gender. It'll update our map and it'll update our data, right? So anything that doesn't have a matching parameter just gets shrunk out of the way. And then everything that does still match gets counted, right? So there are 4 women who were born in Paris. And we can keep digging further if we want to know the women that were in Monaco who were aristocrats, we can keep digging further and further into that set of data. This is, for someone like me, this is really useful and really helpful. It's an easy way to kind of cut through this data and visualize it in some other different ways. Another view is the timeline view. This is counting, counting by number of people and their birth date. So we're just getting a very simple bar chart. But again, we can cut through the data by drawing on the timeline and either march through time and see how the map changes, or just find a spot that we want to look at and spend some time there. And then somewhat similarly is time span. So this is date of birth and date of death. So here's your Priestley view of the timelines. Again, you can draw on this and see the corresponding people on the map. It also highlights the time span that you selected. You can also grab larger periods. So if you wanted the whole early 20th century, you could do that and then drag this around and see how the map changes.
So does that program know all the name of the city and the word or do you need to?
So you'll have to geocode the data. Yeah. So, and there are ways there's some fairly easy ways to do that. Google Spreadsheets, for example, has a really pretty easy way to do that. There's a plugin, I think it's called, what is it called? I want to say it's like Awesome Table or something like that, that you can install on top of Google Spreadsheets, and you basically highlight the column or columns. So if one column is state and the other column is city, you highlight the columns you need and tell it to go, and it'll find all the latitude and longitude coordinates for you. There's ways to do it in programming languages also. R could do it. Python could do it. So there's some other ways to get around it. Any other questions? Okay. I'll also show the graph view. So the graph view, as I mentioned, is the network. So in this case, let's say we wanted to look at people, name, and let's say we want to know their position referring to aristocrat, artist, and so on, banker, merchant. You'll see Palladio do this crazy dance in the background. Oops. But what Palladio gives us is what's called a force-directed network. This is also known as a bivariate network in the sense that it's bidirectional in the sense that it's by position and person. It's not person to person where it'd just be a single network. But it's a fairly easy way to start looking at these networks and seeing that there are people who are both managers and aristocrats. There might be some names in here some of you recognize. Balzac, Ian Fleming, James Bond. It's a fairly basic network, though. You can't do like complicated network statistics on this. If you're interested in something like that, come talk to me. I've got some tools for you. But if you need a simple network, this is one way to do it. Just to show real quick how these other two views work. The table view is, again, just a view of the data. So if we said name, and then wanted to look at gender, position, and place of death, we can see that data. Where it might be useful is if you're still doing stuff in the facet view. So if you wanted to see everybody that was in Paris, it'll update the table for you, and you can look at the data that way. Then finally, the gallery view, which I've honestly not found all that useful, but it might be just to show you there is an image URL that you can include in here. So if you need a kind of visual representation in this way, there's a way to do it. Now, there's one big downside to Palladio, which is that it's very hard. There's two. One is this is all happening in browser memory, which means that if you close your browser or your computer dies or you accidentally hit the back button, all your work goes away. So One way around that is, of course, the download button up here. What that will do is download a .palladio file, which is basically just a JSON file. It's a JavaScript object notation file. With that file, though, any change that you've made to your data, any visualizations that you've built, if you download that as it exists in some state, you can come back to Palladio, re-upload that file, and everything will be persistent. But there's no way right now to really embed these visualizations someplace else. You can take screen captures and embed them that way. There is a way to download the map data with its export button right here. And you'll see I get this .svg file, scalable vector graphic. The problem is that there's no base map, it's just the data. So you'd have to put it on top of your own map. But it could be something you can do if you had to. All right, any questions about Palladio? I know that was super quick, but you play with it, it's cool. And if you have feature requests, let me know, because I'm constantly bugging them about new things. Yeah?
Is it just a world map, or you can input other types of maps?
Like historical base maps?
Or maybe even like a map of the solar system, or
Mm.
something like that.
Like kind of state or county?
Yeah, there is. So to think about solar systems, I don't think there'd be a way to do it that I can think of right off the top of my head. I can think about it though. But if you do have if we look back at this new layer tab with the maps, you'll see there are different data types up here, or different map layer types up here. One is called tiles, which is just pre-built base maps that they provided. So if we wanted like building areas, we could do that. You can include custom tiles. So if you have geodata on a server somewhere, you could pull that in. As long as it's so if it's a WMS file or a map box ID layer, there'd be ways to pull that in. As long as it's on a geo server, which is always tricky. You can also include shapefiles if you convert it into a GeoJSON file. So if you had like county boundaries, for example, or state boundaries, if you convert that into a web JSON object, you could pull that in here and do that. I wish I had an example. I don't. Okay, any questions, thoughts, concerns? Okay. The other one I want to point out is something called raw graphs, which just rebranded itself. It used to just be raw. Raw graphs is built by, I think, an Italian design company called Density Design. You're going to note that it looks sort of like Palladio, and that's because the designer that worked on Palladio also worked on this. I'm not being a shill for Stanford. I'm just saying they're good. So if we look at this, let's see. Let's start here. So this first part should be pretty familiar, right? It looks like Palladio. You drop in your data file in here, or you can upload it or pull it in from a URL, or try a sample. So let's look at a sample. Let's do cars. So it'll read the data in, and it'll parse that data for you. You can see that there's been 400 records in here parsed, and there's no problems with it. If there was a problem, like an extra comma, it would let you know, and it would let you know what line the problem is on. So you can try to fix it. Once your data is ready, raw graphs gives you all sorts of different ways to try and visualize this data. It's kind of up to you to decide what graphic would work best for the data that you're working with. We're looking here at what? Cars, miles per gallon, power, weight. Maybe not the most interesting set of data, but we could do, let's say, I wonder if we can do a bump chart. Let's try a bump chart. Bump chart's a stream graph, basically. Oops, sorry. So you select one of these, and then down below it's going to give you the dimensions. So there's usually a group Group here refers to, I think, the way it's going to color this data. And it's going to try to identify those groups for you, as long as it's categorical data. In this case, it might be car manufacturer, it might be type of fruit, it might be anything that has kind of discrete values to it. I don't think I have anything for that. Name, maybe? We'll see. There's date information. In this case, it's just a year. It's a number. And then size could be, wait. Let's see if this works. Fingers crossed. And it's unreadable, but it worked. Let's clean that up. There. Not interactive, but it is a way to sort of build these visualizations rather quickly. And again, you don't have to know any programming languages or anything like that to get started with them. There's tree maps, as we talked about earlier. There's pie charts. Just don't use that one. Scatter plots, of course, are always good. So if we did, let's see, year, miles per gallon, maybe that'd be useful. But play around with this. There is sample data in there to see what you can get out of it. Raw, I think, does a better job of getting things out, if I remember right. Yep, so you can either embed it, so it'll give you the full SVG code, so you can throw it on a website if you want to. But you can also download different types, including SVG, PNG, image file, and the data model itself. Yeah, so some different ways that you can get that out and take it with you. I think there's anything else. Okay, yeah, I think that's about it. So those are two sort of web-based ways of doing this. We talked about Tableau, if you're interested in that. If I had my computer here, I'd show you R for a minute, but I don't have it here. Let's open the editor of examples. I spend a lot of time in R now these days because it's great. And you can do some really nice statistics in it, and the visualizations are awesome. So I do want to point out D3. I said before that you could visualize this stuff in like any number of ways, and I just want to point out that D3 can do a lot of different things. The community around D3 is incredible. These are all community examples for the most part. Mike Bostock, the creator of D3, is doing this full time. This is what he does now. Mike was formerly at the New York Times. He was part of their graphics department. So a lot of the things that you see the New York Times building, their maps and their other interactive charts that they do, it's D3. So it's a good tool to have in your back pocket. What else? Yeah, and so he's working on this full time. I know the latest version of D3 is trying to make it even easier to get started. I haven't spent a lot of time with version 4 yet, but it's getting better. And like I said, I know Mike's working on it full time now. And then, just to give you a sample of what you can do with it. See if this still works. I don't even know. Okay, good. So this is a map I made with Cameron Blevins, who was a PhD candidate in history at Stanford while I was there. These are, just to give you an example, these are post offices. These are 19th century post offices in the US West. The bar chart on the bottom shows how many post offices. The stack refers to the bottom are how many opened, the top is how many closed in that year. This is completely interactive, so we could zoom in on some of this data and update the map. And then, of course, highlight any one of these points and see what's going on. And it's all D3, right? This is all JavaScript, all web-based. Took a year of work, but That's okay. Anyway, that's all I have. Thank you again. Again, if the guide is up, hopefully you all got the URL. And if you have any questions at all about doing any of this stuff, if there's things I didn't get to show you but you want to know more, let me know. We can talk. All right? All right. Thank you.